Okay, so like we mentioned last time, an involution is a permutation that can be written as a product of disjoint transposition and fixed points. So the identity permutation is an involution. And at the bottom of the page, we have the list of 10 involutions in S4, each written in a one-line notation. And on the top, we have 10 tableaus of the 4 entries. And we'll see in a little bit a correspondence, a bijective correspondence between these objects. Now, this result in red in the middle of the page, like Don Knuth puts it, is by no means obvious, and there's probably no simple way of proving it. But we'll try to give you the idea of the proof in this lecture. Okay. So this RSK correspondence gives it's a correspondence between the set of permutations sigma in Sn and the order pairs of Young tableaus of the same shape with entries 1 to n. Okay, and the idea of the to go from the permutation to the order pair, it goes as follows. So we write the permutation in a tone line notation, 1, 2 up to n on the top first row, and sigma 1, sigma 2, sigma n on the second row. And then we start with our tableaus P and Q empty. And then we insert elements in these tableaus according to the following rules as I goes from 1 to n in this order. So we look at the first entry on the second line here, the sigma 1, and we insert that into the tableau P, and we keep track of the position st of the newly filled position in P, and in that position we insert in Q the element I corresponding to that sigma. So it's best perhaps to do this on an example to see how it works. So let's say the permutation sigma is permutation in S5. And so the entries on the first row are 1 to n, 1 to 5, and the entries on the second row are the sigma 1, sigma 5. So the first entry that we look at, this is 4. So let's put here the P, and the other side, the Q. So P will start with an entry of 4. So I'll just put it here. And corresponding to that, Q has a 1. Then the next element coming along in the second row is going to be 5. So now 5 goes here. So from 4 we get this new tableau 4, 5, and so the new position is position 1, 2, and that's where we add the 2, which sits above the 5. Now the next element is going to be 1, and now we have this bumping happening. So when 1 comes along, 1 bumps 4 from the first row, and that 4 goes on the second row here. For our tableau on the right, the 3 goes in the same position. Okay. Now we have the element 3 that comes along, and we have another bumping happening. 3 is going to bump the 5 from the first row, and the 5 goes on the second row right after 4. And for the other tableau, we have a 4 over here. And then the last entry, we have a 2. And I'm running out of space a little bit here. So let me just erase this one here and draw it over here. I have 1, 2, 3, 4. Okay, and now the element 2 comes along, and it will bump the 3 from here. So we have a 1 in the first position, and now 2 comes here. Now 3 gets bumped to the second row, and it bumps the 4 from their position. So it's 3 and 5, and then 4 goes to the bottom, and the 5 comes here. Okay, so this is the order pair. So the order pair that's associated to this permutation sigma consists of this Young tableau P and this Young tableau here Q, which have the same shape from this rule of construction here. So that's pretty easy. But now, how do you know if this is a bijection? Well, you can go backwards. So one can go backwards if we are given a P and a Q. We can run this algorithm backwards, and we can get a permutation sigma in Sn. I will describe this again by means of an example, so I won't give the whole proof, but let's just say that P is the following: 1, 2, 5, and 3, 4. So that's our P, and our Q has the same shape, and it's 1, 3, 4, 2, 5. And over here on the right, we are going to write the permutation sigma. So the way it works is we start with Q, and we look in the position of the largest element, which is this 5. So we're trying to figure out what was 5 mapped to. And now the corresponding position in the first tableau is 4. And how this is the last position that was filled in P, and how did that happen? Where did that come from? Well, 4 must have come in the previous tableau and must have bumped something from the first row and ended up on the second row. And you can work it out fairly easily that the 4 must have bumped the largest entry from the previous row that is less than 4, and that is the 2. So the way the tableau looked before was in this form, and so the 5 must correspond to this 2. So this was the 2 that came into the tableau at the last step, and it corresponds to the entry 5. Now on the tableau Q, the 5 is gone now. So what we have is 1, 3, 4, 2, and we repeat this argument with the largest entry, which is now 4, and we look at 4, and the 4 as the corresponding entry on the other tableau has to be 5. And now in this situation, this is easy. That 5 didn't bump anything, so that's the entry that must have showed up to increase the tableau. So this is the 5 here. And now the tableau that we have is 1, 4, 3, and the other one is 1, 3, 2. We look at the largest entry, which is 3, and that one corresponds to this entry 4. And again, we're in a similar situation as before. So that must have, that was the number that must have arrived into the tableau the previous step. So that's a 4. And our tableau will be a 1 and a 3. And the other tableau here is a 1 and a 2. And now we're all almost done. We look at the largest entry, which is 2. So we have a 2 here. And that corresponds to this 3. Well, how did the 3 ended up there? Well, in order for it to end up there, it must have been the element that, like the previous 3 must have bumped a 1. So no, the previous element that came here was it was a 1, and so in this situation we have 2 goes to 1, and the remaining tableau here must be 3, and the remaining tableau here must be a 1, which now gives us the 1, and it gives us the 3, and this is the permutation. And I leave it to you to, if you wish, to go to double check that if you go from sigma, if you start the sigma, you start this process and you go down, these are the tableaus that you get. The P will be the one here, and the Q will be the one here, just to make sure that we didn't do any mistakes. But so what this shows is that, again, we have this this bijective correspondence of sigma in Sn with all these order pairs PQ of Young tableaus of same shape. Order pairs of the same shape with entries in the set 1 to n. Okay, so this is quite important. And from here, you can get an identity that the number of elements on the left-hand side, which is n factorial, equals the summation of number of tableaus of the same shape. Let me just write f lambda, where the lambda is the shape of the tableau, squares over all lambda partitions of n. Okay, so that's some identity that you can get for free from here. Now, what other properties does this formula, does this correspondence have? So here we saw that this permutation sigma 45132 leads us to these two tableaus P and Q. What I will show you now is that if we take the inverse of the permutation, then that will permutation sigma, that will the order pair of the tableau of tableaus that correspond to it is going to be Q and P. So remember these formulas here. So I'll write them down on the next page. Right here. And basically sigma corresponds to P and Q, and what is going to happen is that sigma minus 1 is going to correspond to the pair QP. So if sigma gives you P and Q, then sigma minus 1 will give you the pair QP. And how does this work? So let me write down the previous example where I had sigma 1, 2, 3, 4, 5, and 4, 5, 1, 3, 2. This gave us the P, which is here 1, 2, 3, 5, 4. So this is the P, and the Q, which has the same shape, but it's 1, 2, 3, 4, 5. And now what I want to show you here is what happens when we look at the permutation sigma, the inverse of sigma, which is we obtain by just flipping the rows of sigma. And if you arrange them increasingly, you get that this is going to be 3, 5, 4, 1, 2. And we are going to do the same procedure here. Let's see what we get. What are the tableaus that we get for P, and what tableau do we get for Q? So again, for P, we start from the second row. So the first entry is 3, and the Q, it's easy, it's a 1. Okay. And then the 5 comes along for over here for in the second row. So that leads this tableau to be changed to 3, 5, and here this is easy, it becomes 1, 2. Then 4 comes along. Okay, and 4 will bump the 5 from the first row, so it 4 goes on the first row and 5 goes on the second row. This one is easy, 1, 2, 3. Now 1 comes along, and 1 will bump the 3 from the first row, and then 3 goes down and it bumps the 5, and then we get this shape. So 1, 2, 3, 4, and the last entry is the 2, and the 2 bumps the 4 from the first row, and then 4 goes down and it goes next to the 3 here. We get this shape, and the other tableau is 1, 2, 3, 5, and 4. And as you can see, what happened here? Did we get? Did I get them mixed up? No, we didn't get them mixed up. These they look almost alike, but this tableau here, this is the Q from sigma, and this tableau here, this is the P from sigma. So the order has switched. And now, so again, this is not proof. It's just, you can call it, I guess, proof by example if you wish. Although several details will have to be sorted out in a formal proof. But I hope that this shows you this property that convinces you of this property that if sigma gets associated to a order pair of tableaus P and Q, the inverse of sigma gets associated to the order pair of tableaus Q and P. So it switches the order. Okay. Okay. So then, how does that lead us to involutions? Well, for involutions, what happened is that in an involution, sigma equals sigma minus 1. So that's a property of its equivalent property of an involution is that sigma equals sigma minus 1. So in that situation, this order pair PQ has to equal this order pair QP, and that leads us to P equals Q. And you have this bijective correspondence between involutions and Young tableaus. So let's do one concrete example to see actually that this is the case. So let's take one of the examples of an involution. So sigma 1, 2, 3, 4, and we have here 3, 2, 1, 4. So this is just a transposition 1, 3. And let's see what the tableaus we can associate to it. So again, we start from with the P. So we have the P here, and we get a 3. And then in the other tableau Q, we put a 1. Then the 2 comes along, and 2 is going to bump 3 down. So 2, 3. And here the new position is the 3. So that's where we're going to put our next entry, which is a 2. And then the 1 comes along, and it bumps the 2 down, bumps 3 down. So it goes like this. So we have this situation, 1, 2, 3. And then 4 comes along, and it just goes on the first row, 1, 4, 2, 3. And similarly, you get 1, 4, 2, 3. So you see that this permutation here being an involution, it guarantees that the P and the Q here are the same. Okay. We can do one more example with a different involution. So let's just write it here. Let's write another permutation tau. 1, 2, 3, 4, 2, 1, 4, 3. This is a product of 2 transpositions. And let's see what happens here with the P and with the Q. So the P starts from on the second row. So we get our 2. We have this different color. So we have our 2 goes here, and the 1 goes here. Then the 1 comes and it bumps 2 down. So we have 1, 2, and the other one, we have the same thing, 1, 2. Now 4 comes along and it just tags next to the 2. And then the last one is 3 comes along. It's going to bump the 4 from the first row, and the 4 goes here. And goes 2, 1, 4, 1, 3 goes there. And what's going on here? So it's 2, 1, 4, 3. So let me see. I have 1, 2, 1, 1, 2. The 4 went there. Okay, yeah, the mistake is here. I shouldn't have put the 3 here, because when, see, what happens is when the 4 was inserted in this position here, the corresponding entry to it above, it was the 3. So this 3 goes here. And now at the last step, we're good. The 3 comes along, it bumps the 4, so on. And then this other one goes like this, 1, 3, 2, 4. Okay, so the same property as before. Okay. So this gives you, again, this bijective correspondence between Young tableaus with n entries of any shape, all of them, and involutions on n elements. And it naturally leads to the following question. I mean, what can you say about this, the number of involutions on n elements? So let's denote by Sn the number of involutions in Sn. And we can do some simple calculation for small numbers. Let's see here, n. S of n. In no elements, you can kind of agree to say that that's 1, but with 1 element, you have identity. With 2 elements, both of them are okay. With 3 elements, you will have identity, and then each transposition will work. So you have 3 choose 2, so you have 3, so you have 4 in total. And then how many with 4? Well, we saw a bit earlier on the first page that we listed 10 of them, and we'll actually show that there are 10 of them. So I'll put it here, 10. Another way, so you can list them all in order to be, such a permutation. You know, of order 4, you either have to be 1 transposition or the identity or the product of 2 disjoint transposition, and you can count how many there are. You have identity, which is 1. So 1 identity plus the transpositions will be 4 choose 2, and that's 6. And plus there will be 3 others that are product of 2 disjoint transpositions, and you get 10. But what happens with 5, 6, and so on? Well, here's a proposition. So we can try to work out a recurrence relation for these numbers. And let's say for n greater or equal to 2, we'll prove that Sn equals Sn minus 1 plus n minus 1 times Sn minus 2. Okay. So how does this work? Well, you take S sigma in Sn be an involution, and we look at sigma n, and we have 2 situations. Sigma n is fixed, so sigma n equals n, or the other situation is sigma n doesn't equal n. So in the first situation, if sigma n equals n, so sigma looks like 1, 2, 3, n minus 1. Here we have sigma 1, sigma 2, sigma n minus 1, and n is a fixed point. So this part containing n, you can ignore it, and you can think of sigma as being a permutation on n minus 1 elements. And because sigma was on n elements was an involution, this permutation on n minus 1 elements is also an involution. And how many such sigmas there are? There are Sn minus 1 such involutions. Yeah, now what happens on the other side? Well, on the other side, if we have sigma not a fixed point, then it must be some, because our permutation sigma is an involution, sigma n must equal some j, and that sigma j must equal n. And now, how many choices do we have for this j? Well, j can be any element from 1 to n minus 1. So we have n minus 1 choices. And then when we ignore what the permutation does to j and what it does to n, we get a permutation on n minus 2 elements. It's not on the set 1 to n minus 2, but the number of such permutation is going to be the same number of the permutation on the set n minus 2. And this permutation is also an involution. It's going to be a product of disjoint cycles of length 2 transpositions and fixed points. So we will have Sn minus 2 choices for such a permutation on n minus 2 elements. And so together, this and this together, they can be paired up in all possible ways. So we get n minus 1 times n minus 2 involutions. And then that proves a result. Our set of Sn involutions has been partitioned into two sets, one having Sn minus 1 elements and the other one having n minus 1 times Sn minus 2. Okay. So with this relation in mind, one can go and calculate, you can fill up more values here in this table of values. Right? This is, you can do 76, 232, 764 for 7 and so on. Now, as far as I know, there's no closed formula for Sn. We'll give a different formula in a little bit. But with this property of the previous recurrence relation, if we define f of t to be the exponential generating function of this of the number of involutions, then one can prove, and give the details in the textbook, so I'm not going to prove it here, that f of t equals e to the power t plus t squared plus 2. Okay, so one can determine the exponential generating function of the number of involutions. Now, there's another formula that we can prove for the number of involutions, and this is as follows. I will give here another proposition for n greater or equal to 2, Sn will equal the summation from k equals 0 to the floor of n over 2 of n and choose 2k times what I write here is 2k minus 1 double factorial, which you can write as summation from k equals 0 to floor of n over 2 of n choose 2k times this 2k minus 1 double factorial. You can write it as 2k factorial divided by 2 to the k times k factorial. Okay. Now, okay, how does it how do you prove these results? Where does it come from? So the way when we are counting when we're counting the number of involutions of order n, we first choose the set on which we have disjoint cycles. Okay, so in order to have disjoint cycles, those cycles are transpositions, they're pairs. So every permutation is going to be something like A1, B1, AK, BK. So these are all the transpositions, disjoint transpositions. And then we'll have a bunch of fixed points. Let me call them C1, Cn minus 2k. Okay. So once you know this this set here, then you automatically know that everything here is fixed. So now in the formula above, what we do first is how large can this k be? Well, k could be as small as 0, in which case the permutation sigma is the identity, but k can go at most as, so 2k has to be less than or equal to n, so that leads to k being at most floor of n over 2. Okay, so that's the range of our summation. And then how do we do the count? Well, first we count the set here of all these, in how many ways can we pick this set of A1, B1, and so on. So we have 2k elements that we're choosing from a set with n elements, and that's n choose 2k. Okay, so now we have these 2k elements, and we have to count them number of ways of pairing them. Okay, so that's what I'll do on the next next page. So we have, let me write it here, 2k elements. What is the number of ways of breaking them into pairs, into pairs? So let's do some simple examples. When k equals 1, you have one pair, so you can write it, so there's one way. It's just one way of doing it. Let's say A1, B1. When you have k equals 2, let's write it graphically so we can think of having 4 points, and we want to break them into 2 pairs. So one way is like this. Another way is like this. And there's a third way as using the diagonals. So in this situation, we have 3 ways. Okay. Now, what happens when k equals 3? So let me write it as a hexagon. Okay. So I can label, if I let's say label these elements as x1, x2, x3, x4, x5, x6. So I want to count the number of pairings. So if I look at x1, it has to be in a pair with exactly one other element. How many choices does it have? Well, if you look, you have 5 choices. So 5 choices for the pair of x1. So the element that pairs with x1. And now once you pair x1 with such element, you're left with 4 elements. And you know that 4 elements, you can pair them in 3 ways. So the answer is going to be 5 times 3, which is 15 ways. Similarly, this works for any k. So in general, for 2k, if you have 2k elements, and you pick one element here, x1, you're going to have 2k minus 1 choices for the pair of x1. And then you're left with 2k minus 2 elements, and the number of pairings of that you can use induction to figure out. And then it turns out that you can prove that the number of ways will be 2k minus 1 by induction times 2k minus 3 double factorial, so which is 2k minus 1 double factorial. So the double factorial, I guess I haven't defined it, is the product in steps of 2. So let me put it here. So 2k minus 1 double factorial is 2k minus 1 times 2k minus 3 times all the way to 1. Okay. So the number here, the answer to our question is 2k minus 1 double factorial. And you can write this number. It's not too difficult to show that this 2k minus 1 double factorial, it's the same thing as this number. It's not too difficult. Okay, so this is another formula. Now the advantage of this formula is that it actually, one can use it to work out the asymptotics of Sn. And when you write down this summation, over here you have these terms, and you can figure out that these terms actually increase with k up to a value of k, which is about half of n minus square root of n, and then they decrease. And I'm not going to give you the details. I'll just state the result, which is, I guess, was done by Moser and Wyman in 1955, and you can find it also in Knuth, volume 3 of Art of Computer Programming. And it says that Sn is about n to the power n over 2 over square root of 2 times e to the power n over 2. Let me write this nice. E to the power n over 2 minus square root of n plus 1 over 4. So it's an exponential growth for Sn, and roughly about n over e to the power n over 2. Okay. All right. So that's how the number of involution grows, and like we mentioned before, the same thing as the number of tableaus of order n. But now, so the last thing I want to talk to you about is, what about if we fix the shape of the tableaus? So let's say we want to count a tableau. So the question is, how many tableaus have shape given by some numbers, let's say n1, n2, and m, where n1 greater or equal to n2 greater or equal to nm greater or equal to 1. So this question was studied by the German mathematician Frobenius, connection to problems in group theory around 1900. So he gave an answer that I'll show you here, and later on McMahon gave a combinatorial proof. So these Young tableaus I didn't mention before, but they're closely related to group representation of the symmetric group. So they play a key role in this area. So this study of Young tableau is quite important in algebra and combinatorics. Now, how would you count? So let's say I give you a shape, coming back to this problem. Let's say we have a shape. Let's say I write it like this: 5, 4, 2, 1. So how many tableaus do we have of this shape? So if we write the tableau, we have a 5 here. We have a 4. We have a 2, and we have a 1. Okay. Now here's the idea. It's a recursive formula. So I will denote this number of tableaus by. So let's denote this number by f of n1 and m. Okay. And here's a observation. If I want to count the tableaus of shape 4 to 1, I know that the 4, so 5 plus 4 is 9, plus 3 is 12. So the 12, there is a 12 on this tableau, And the possible value positions for 12 would be here. These positions are what are called corners. So a corner is a position on the tableau that doesn't have anything to its right and doesn't have anything below it. So this is a all these are 4 corners. And so 12 could be there, or 12 could be here, or 12 could be here, or 12 could be here. So if 12 were to be here, then the number of tableaus is the same as if we remove 12 from that position, and then we end up with a 4, 4, 2, 1. Similarly, so that comes from here. Similarly, if we have 12 in the position 2 and 4 over there, that will leave us with a tableau of 5, 3, 2, 1, plus if we have 12 in the position 3 and 2, that will leave us with a 5, 4, 1, 1, plus if we have 1 at the end, at the bottom, we would have a 5, 4, 3, and technically a 0 there, but by convention, we can say that that's the same thing as 5, 4, 3. So this is a key recurrence relation that the number of tableaus satisfy. And yeah, it's basically based on the fact that, so this recurrence relation is that a tableau with its largest element removed is a tableau on the remaining set of elements, n minus 1, something like that. Okay. Okay. So this function f of n1 and so on has these properties. So f of n1 and m is 0 unless we actually have a tableau that could possibly correspond to it, let's say greater or equal to 0. So we extend it to entries which are greater or equal to 0. And then we use this, we agree that if you have a 0 at the end, it's the same thing as if you remove the 0. That's easy. And m here. And the third property is what I just showed you earlier, that if you want to calculate f1 and m, you can just do f of n1 minus 1 and 2 and m plus f of n1 and 2 minus 1 and m. You can go all the way to the end, f of n1 and m minus 1 and m minus 1, like this. Okay. All right, so that's basically it. And now, so this will lead to a formula for f, for this number of tableaus of this shape. To describe this formula, let me I need to introduce a Vandermonde determinant. So let's say if we have x1, xm, you can take them real or complex numbers, it doesn't matter. We define this determinant x1, xm is defined as follows. The first column are powers of x1, so x1 to the power m minus 1, x1 to the power m minus 2, going all the way to x1 to the power 1, and here at the bottom we have a 1, x1 to the power 0, and we can do the same thing here with x2. I'll just remove the power, it's pretty clear. Okay. And then it goes like this until the last column is xm to the power m minus 1, xm to the power m minus 2, xm and 1. And now it's known, so this is what is called a Vandermonde determinant. And one can prove, you can do induction on M if you wish, that this determinant, delta x1 xm, equals the product over all pairs I less than j from 1 to m of xi minus xj. So I'll leave it as an exercise for you to prove this. Okay, so that's our notation for this Vandermonde determinant. And the result, so we have two ways of formulating the results. So again, I won't give you the whole details of the proof, but from these recurrence relations, you can deduce that. So I guess this is Frobenius. You can deduce that the number of tableaus of shape n1, n2, and m will equal the following, will equal this Vandermonde determinant of the numbers n1 plus m minus 1, n2 plus m minus 2, all the way to nm, divided by n1 plus m minus 1 factorial, n2 plus m minus 2 factorial, all the way to nm factorial, and times n factorial here. So this is one formula for the for this number of, and it's a very nice formula for the number of tableaus of this shape, of this form. It's the same as a formula which involves what are called the hook lengths. So I will write it to you. I'll explain what hooks are and their lengths below in terms of an example. So we had this previous partition of 5, 4, 2, 1. So let me draw it here. Okay, so we have 5 in the first row, 4 in the second, 2 and 1. Now, a hook is you pick an entry and you look at what you see to the right of it and what you see below it. And if you add up the number of the squares, including the square itself, you get the hook length. So in this situation, so for the position, let's say 1, 1 here, the hook length would be, let me use a different color. So for this position 1, 1, the hook length would be h1, 1. And what is that? You have, that would be 8 in this case. Okay, because you have 5 going to the right and then 3 below. Okay, and then here, what do we have? We have h1, 2. That would be 6. Here you have h1, 3. And that is 4. And then here. So the easiest way is to just write these hook lengths in the squares. So I'll just do that here. I'll write here the value of the hook length, 8. What was this one? 6. This one is 4. You have 3. You have a 1. Now below here, we have a 6. Here we have a 4. Here we have a 2. We have a 1. And then over here we have a 3, a 1, and so the other formula for the number of Young tableaus of this given shape is in terms of the hook lengths, and it says that f of n1 and m will equal n factorial divided by the product over all entries ij in the tableau of the hook lengths ij. So for our problem here, the number of these tableaus of shape 5, 4, 2, 1 will be 12 factorial divided by the product of these hook lengths, 8 times 6 times 4 times 3, 6 times 4 times 2 times 3, which is also the same as the formula that we have here with the Vandermonde determinant.